Welcome. In this short video lecture, we are going to describe how to find minimal polynomials of our square matrices. So my tutor, please, if you have not subscribed to my YouTube channel, please subscribe so that you can always be getting updates on the upcoming math classes. So let's go directly into the class. So let's start by an appetizer. So appetizer. Find the minimal polynomial for the matrix given by 1, 1, 0, 1. So one thing that you have to remember in mathematics, you can't answer a problem if you don't know the definition of the meaning of the thing that you want to calculate. So if I may remind you that minimal polynomial for square matrix is harmonic polynomial. So minimal polynomial is monic, so which means that the leading coefficient must be 1, and then of lowest degree, and then such that the matrix A satisfy that given polynomial. So let's describe how we find all these properties that defines or specify the minimal polynomial for this specific matrix. So what you do, the first thing, step 1, find the characteristic polynomial. So this will be the first thing to do. So remember, characteristic polynomial will be given by determinant of lambda I minus A. So for this case, we'll have, so this is characteristic polynomial of the matrix A will be given by lambda minus 1, 0, 1, lambda minus 1. Determinant of this matrix, we tell us that characteristic polynomial will be lambda minus 1, lambda minus 1, because simply this product here is 0. So you may expand and get lambda squared minus 2 lambda and then plus 1. So there are two possibilities. So remember, minimal polynomial always divide a characteristic polynomial. So possible factors of this polynomial is actually lambda minus 1 and lambda minus 1 squared itself. So therefore, we say that here we have two possibilities. For the minimal polynomial, MA of this matrix, i.e., it can either be, say, a function f of x given by just the structure of this one, x minus 1, x minus 1, the same as x squared minus 2x plus 1, or it can be a function or a polynomial of the form g of x equals, so the factors of this characteristic polynomial is the characteristic polynomial itself and factor of this form, or simply in terms of lambda minus 1. But remember, minimal polynomial is unique for a given square matrix. So therefore, we have to test if either f of x and g of x satisfy all the properties. I remember by Cayley-Hamilton theorem, always the characteristic equation, the characteristic equation, every square matrix satisfies its characteristic equation. So let's say by Cayley-Hamilton theorem, f of a equals to a squared minus 2a plus 1. Actually, so when we have numbers, so remember these are matrices, so then matrix form we just multiply by identity. It's always a zero matrix, so there's no problem on this characteristic polynomial. So we have to test to check whether g of a is zero matrix. So remember, when we say g of a, simply means according to the definition of g, you'll have a minus. So this is number, but so in terms of matrix multiplied by an identity, so minus I. So which will give us 1, 1, 1. One, 1, 0, 1 minus the identity matrix 1, 0, 0, 1, which will be 1 minus 1, and then 1 minus 0, 0 minus 0, 1 minus 1. So which will give us 0, 1, 0, 0. But you see, this is not a zero matrix. And because every square matrix satisfies its minimal polynomial and this one is not satisfying, then g of x, x minus 1 cannot be the minimal polynomial. So therefore, the minimal polynomial for a is just the x squared minus 2x plus 1. So just write ma of x. I remember another person can actually use the polynomial in terms of lambda, so it can be ma of lambda equals to lambda squared minus 2 lambda plus 1, still have the same meaning. Then example 2, find the minimal polynomial for the matrix B given by 3, 3, 0, 3, 3, 0, 0, 0, 6. So the same three things must be tested. That should be monic, should be lowest degree, and then should satisfy the matrix should satisfy that given polynomial. So solution, step 1, characteristic polynomial. And you find characteristic polynomial. So characteristic polynomial of this matrix B is obtained by determinant lambda I minus B. So which will be determinant of lambda minus 3, 3, 0, 3, lambda minus 3, 0, 0, 0, lambda minus 6. So this is a characteristic polynomial of our matrix. So these are determinant 3 by 3 determinant we use this for. So we'll have lambda minus 6 times the submatrix lambda minus 3, 3, 3, lambda minus 3 equals to 0. So lambda minus 6, lambda minus 3 times lambda minus 3 minus 9 equals to 0. Not equals to 0, so they're not equating to 0. So that's a mistake. So this is not an equation. So characteristic polynomial is lambda minus 6 into lambda squared minus 6 lambda plus 9 minus 9, which is just the same thing as saying lambda minus 6 into, so 9 minus 9, 0. So lambda squared minus 6 lambda. So this can be written as lambda cubed minus 6 lambda squared minus 6 lambda squared plus 36 lambda, which is lambda cubed minus 12 lambda squared plus 36 lambda. So this is a characteristic polynomial, or you can write it as a characteristic polynomial of this matrix B is lambda into lambda minus 6, lambda minus 6, which is the same as lambda into lambda minus 6 square. So it is from the characteristic polynomial that we can determine the minimal polynomial by simply listing all the possible factors of the characteristic polynomial and then testing whether those different combinations will satisfy the property that when you put in the matrix, then it satisfies that equation. That simply means that when you replace, you get 0. So a 0 matrix for that case. So here are the possibilities. So the possibilities are, we can say g of x equals to, I can actually just take lambda because it's a factor of this. Lambda, so g of x will be now x, or say lambda of g of lambda equals to lambda. Then say f of x equals to another factor of this one. You can say lambda into lambda minus 6. And then say h of x, so this is x, equals to say x minus 6. And then say r of x equals to x minus 6 squared. But this one, what we know is that when you put the original matrix into the characteristic equation, which will be B into B minus. Now, these are numbers, so you have to multiply by an identity matrix to show that, which is the same thing from what you have gotten here as B power 3 minus 12 B squared plus 36 B. So this is always give us 0 from Cayley-Hamilton theorem. So there's no need for us to prove that. So that satisfies the condition that when you put in the value of the matrix, you get 0. So, and then what we know that, so G of A, the G of B will just be given by, so the matrix itself is 3, 3, 0, and then 3, 3, 0, 0, 0, 6. Obviously, this is not the same as 0, 0, 0, 0, 0, 0, 0, 0, 0. So this implies that G of X equals to X cannot be a minimal polynomial, because it doesn't give us a 0 matrix. So the next possibility, so then this one have ruled it out. Our next possibility, this one here, so f of B will be given by B into B minus 6. Now, this is a number that you have to multiply by an identity matrix to be matrix form. So this will give us B, which is 3, 3, 0, and then 3, 3, 0, 0, 0, 6 into 3, 3, 0, 3, 3, 0, 0, 0, 6. When you multiply 6 by an identity, you'll have 6, 0, 0, 0, 6, 0, 0, 0, 6. So f of B will be 3, 3, 0, 3, 3, 0, 0, 0, 6. So corresponding also 3 minus 6 is minus 3, and then 3, 0, 3 minus 3, 0, 0, 0, 0. So this multiplication, usually row by column, will give us so this will be 3 by minus 3, that's minus 9, plus 9, 0. 9 minus 9, 0, 0, 0, 0. Minus 9 plus 9, 0 times 0, 0. 3, 9 minus 9, 0, 0, 0, 0, and then 0. So actually, which should be the case that f of the matrix should give us a 0 matrix. So therefore, f of x equals to x into x minus 6 is a minimal polynomial. So because it satisfies the condition f of the matrix equal to the 0 matrix, then it is the only minimal polynomial because they are unique. So even if you test for the other one, you still not get 0. So that is the minimal polynomial of the matrix is x into x minus 6, or you can say x squared minus 6x. So this is the answer. Remember, another person can use variable, take lambda to be the variable. So you can as well say f of lambda equals to lambda into lambda minus 6 is the same as lambda squared minus 6 lambda. is a minimal polynomial. So there's nothing special with that. We can decide to use lambda throughout as a variable. So that is what we get for that given problem. So try this. So try this exercise. So find the minimal polynomial of each of the following matrices. So the first ones so 1, we have 2, 1, 1, 2. Number 2, 1, 2, 3, 4. Number 3, 4, 1, 1, minus 14, minus 4, minus 6, 5, 2, 4. Number 4, 3, 0, 1, 2, 2, 2, minus 1, 0, 1. Number 5, 2, 2, minus 5, 3, 5, minus 15, 1, 2, minus 4. So in case of any question, or if you experience any difficulties in solving any of these questions, please don't hesitate to contact me via email or WhatsApp. So my email is vcnandua@unbi.ac.ke, or you can send me a message on WhatsApp. Then can help you on how to go about such problems. So thank you.